Hi guys. So I'm getting a question in from Remind, and just if you're here on the Zoom with me, because I only have one device that I'm running the Zoom through, I can't see the chat at the same time that I share my screen, or maybe I'm just technologically challenged here. But if you guys can ask the questions on Remind, I've hit record, so I'm gonna go ahead and share my screen now, so I won't be able to see any chat questions on here. So give me a moment to share screen. Okay, the first question I have here is, how do you find the limits of integration when you're given an XY graph with numbers instead of angle measures, and limits of integration in general? So, yeah, and I can't hear you guys, or I can hear you guys. Can you tell me if you guys can see the screen?
We can see the screen.
Okay, thank you. Okay, so in general, I think to answer that question about how you can find the limits of integration on an XY graph, I'm not sure I understand the question, but if you're just looking at, let's say I pull up, oh no, I put that in geometry. If I pull up the notes from today, so there was one question on, okay, so like say you guys are given a graph like this and you're asked for the limits of integration. I think one of the skills you have to have when dealing with polar is having an idea of what angle measures get you certain points. So in my mind, if I'm given this graph, for example, and it was the AP test, the graph is typically given to you guys on the free response. Or if not, it's one of the basic graphs like the rose curves. And so I'd be familiar with how to do the min max strategy that I gave you guys in class. And if that's one of the things that you're struggling with, you can also let me know on Remind and I can review it with you guys again. But if you're given a graph like this that's like irregular, what I would suggest doing is working with this equation. And although you have the calculator, a couple things you guys can do. If you don't have the calculator, I would plug in a couple of values for theta. In my mind, I don't write it out. I just think, okay, well, what is 0? If I plug in 0, I get 0. So at angle 0, my radius is 0. At pi over 2, if I plug pi over 2 in, I get pi over 2 plus sine of pi, which is 0. So pi over 2 is approximately this coordinate point right here. And so lastly, if you plug in pi, you'll get this point right here. So what I'm, I think I accidentally hit the Zoom, hold on. Okay, so if I'm thinking about these in terms of sectors, so let's say this is through pi over 4. So at pi over 4, this is the coordinate points I should see. So as I plot the points up till pi over 2, I should see the area for this from 0 to pi over 2. And what that left coordinate point tells me is that by the time I get to pi, these angle measures right here, all these coordinate points that I'm not plotting, but I have a general idea of how it works, that it then spans all of that till pi. So I know that for my limits of integration for a graph like this, I should go from 0 to pi. There was one that we did on Parametric. It was the very first one that was the cardioid. Again, for that one, in my mind, I'm mentally just doing what is the radius at 0 at pi over 2 pi and 3 pi over 2 roughly to see what part of the graph it sketches out. And if that's sufficient, then that's where you would go with it. If you want more details, you have a graph and you're not too sure what how you get the limits of integration to form the area of the specific curve that you're given, I would play around with the window on the graphing calculator. So remember, you guys have access to a graphing calculator. It's just knowing that when you're experimenting with what the curve looks like, that you're in polar mode, but then after that, you really don't need to be in polar mode. So for me, a problem like this, I'm not going to graph it if I have a good sense of the idea of knowing what the coordinate points are at 0, at pi over 2, and pi, and that from 0 to pi, it gets me the region that I want. I don't really need to switch to polar mode and waste time to graph this when I am clearly given the values for theta, and it's also written in here as well. Now, for the rose curves, you do want to plot a few points if you need to, but understanding when it reaches the maximum petal, minimum petal is important, and even doing 2 rounds of the minimum petal so that you know, okay, when it starts off at 0, then goes to the max, when does it come back around to 0 to get the full petal? Hopefully that answers the question. I'm not sure Brendan's on the call, but that's generally how you would do it. Luckily for you guys, is mostly on a graphing calculator. So let me double check on Remind again. Again, if you're just joining, if you guys can direct your questions onto Remind, that would be helpful. Oh, the 2 questions before the 2013 free response, sure. I think one of them was an open-ended question about like name 2 ways to find the area of a petal. So I remember when I gave that quiz out, I had quite a few responses. So technically there's an infinite number of ways to set up an integral with petals, including, you know, finding the petal that might not be in the first quadrant, but maybe in the second and third quadrant. So I remember I got lots of different responses for that. So the responses that I show are just some common ones, and don't feel like you have to not understand, but get all of those to get it correct, because there's an infinite number of answers. So yes, I can post that if you guys would like. And the question is the 2 questions above the 2013 for response, which you guys can find on the chapter 9 review, which was assigned last Friday. Are there any other questions that you guys would like me to go over? Renee also pointed out that in a prior video I had that I recorded for, let me see which free response it was. It was for the, if you guys are looking at those videos, the 2013 free response on polar, which I can pull up here. Let's see if I actually have the work from previous years. Here, let's see. Yeah, I'm not sure. So apparently in the video, which I cringe whenever I have to rewatch a video, so I try not to. For the 2013 question 2, part A, if you guys watched the recording, and I'll make a note of it beside the link to the recording, I might have not gotten 24.709, and I'm not sure why. Someone pointed out that I might have said 19.996, which without watching the video, I don't know how I got that, but this is the correct answer right here. And this is a question that was attached to your chapter 9 packet. The last 2 for response is just extra practice for polar. And so if you were in class today, these are the 2 questions I'd like you guys to attempt to before your free response tomorrow. So let me just double check. I see some questions coming in. Yes, one of the questions is relating to a general question. So let me come back to that. Let me see if, oh no, there was a mistake for part B and C as well. Can you double check to see if, okay, well, maybe I'll delete that video just in case I don't want to have any misconceptions. And if needed, I can re-record a video of how to do the problems. But someone is saying that 2013, there's a mistake on B and C. So I'll take a look at that, and then I might have to swap it out, or maybe I'll explain it in a separate video and post it if you guys need. Okay, so going back to the min-max petals, let me do one of the questions that was, okay, so this one. So you guys are given a rose curve. So I only do the min-max discussion when we do rose curves. So with rose curves, let's say for this one, if they just want 1 leaf or 1 petal, the maximum petal length is the amplitude of whatever your trig function is. So in this case, we know that cosine of 2 theta has a maximum of 1. So the amplitude being 3 means that that maximum length of that petal is going to be equal to 3. So 3 is what I would set my initial equation to be. And when I solve for it, I get cosine of 2 theta equals 1. At which point you're asking, when does cosine equal to 1? When is cosine equal to 1? And that's at 0. So we set it initially at 0 and we get theta equals 0. The next iteration would be cosine of what angle gets you 1, and it could be -1 as well. That's okay. So in this case, that would be at pi, which I know gets me -1, but that's okay. So theta equals pi over 2. So that's the second iteration of it, or 2 rounds of finding the max petal. For the minimum petal length, well, the minimum being when does it go back to the pole, which is the origin. And so the minimum petal length is 0. When you guys set that equal to the equation divide by 3, you get cosine of 2 theta equals 0. And 2 theta must be equal to pi over 2, because cosine of pi over 2 is equal to 0. And so therefore at pi over 4, we have the minimum petal length of 0. So the way that works out is my smallest angle here is 0, and it reaches a maximum petal of 3. So 3, 0 is one of the coordinate points. So at angle 0, you have a length of 3. And then after 0, the next highest angle is pi over 4. In my calculations here, pi over 4 would be next. And at pi over 4, it means that it's wrapped back around to 0. So the way that I want to picture these sectors is at 0, it was here, and then an angle close to 0, close to, what was it that we said? Was it pi over 4? So by the time you guys get to pi over 4, it wraps back around to 0. So this etches out a half petal. And if the half petal happens to be in the first quadrant, then the rest of the petal must be in the fourth quadrant down here. So the angle measures that get us that. If we wanted to integrate for this full petal, we would think of it as pi over 4 would be the top limit of integration. And then the bottom limit of integration would be negative pi over 4. So if I were to go from negative pi over 4 to pi over 4, 1/2 r squared, whatever r might be up above, this would get me the full petal. However, if I did 0 to pi over 4, 1/2 r squared, I would make sure that I double that, because that would only get me half a petal, so I have to double to account for the half area. Let's see, there's a few questions in period 5. Let's see. Okay, 2003 for response here. So if you guys look, I think this one's a tricky one because it looks like it's polar initially when you look at the problems, but then if you look at the equation is in rectangular. So we want to think about this in terms of rectangular. And so if you guys look at the first question, well, go ahead and read through if you guys haven't read through it. And then look at the first part of it. It's asking for set up an expression involving one or more integrals with respect to x that represents the area. So with respect to x automatically means that this is not polar. With respect to theta, it would be polar. So for this one, I'll just discuss it with you guys. But in terms of x, now we have to switch back our thinking to function mode, which means that we're summing up rectangles instead of sectors. I know it makes it confusing. So we see that the intersection between these two circles is at x equals 1. The first part of the rectangles that you guys have would be here. And then the other part of the rectangles would be over here. So we see that the top minus bottom requires the use of two different equations. So this one, for this section right here, you guys need this part of the circle. Whereas over on this side, you guys need this side of the circle. So the equation is in terms of x because the width is x. And you're setting this up like you guys learned in chapter 6, which means that you have to solve for what y is equal to. So 2 minus x squared for one of the equations, and then the square root of that. The other equation would be y equals 1 minus x minus 1 squared, and then the square root of that. And then you're going to do top minus bottom. For the person who asked this, does that clarify for A? And then for B, what you want to do is do right minus left instead. So this one is right minus left. And then also in terms of y. Can the person who asked this confirm that that's enough information to get started on that question for A and B? And as that person is answering that question, I'm going to answer part C, which is the part that is polar. Okay, so in question C, they switched those equations that were above initially in rectangular to polar form. So I can see that r equals square root of 2 must be, and I'll color code this so we can see, r equals square root of 2 is the circle centered at 0, 0 with a radius of square root of 2, which is 1 point something. So hence you guys see the radius there. And then the other circle here is this circle in pink. And that must be r equals 2 cosine theta. So when I look at this region, I can see that this part of it is geometrically a quarter circle. So you don't have to use any calculus to determine the area of a quarter circle. You just do pi r squared. In this case, r is 1, divide by 4. And then that's part of the area. What you then need is the other part of the area of region R, which is this part. And that part of it can be found using just this portion of, sorry, that's the same color, just this curve here. So what we want to do for that one is identify the curve, which is the yellow curve. And if we etch out the sectors, remember it's important that you guys find out what the intersection point is of the two circles. And then from there, if you were to integrate from this coordinate point to this coordinate point, you would get this pizza slice here. And so I'm trying to think, now I'm thinking that maybe we don't do the quarter circle, but we do that red region plus the little kind of like crust that you guys see above there. Let me do a different color. Let me erase this actually. So let's actually first find the intersection of these two equations. So the intersection involves setting it equal to each other, dividing over. So cosine of theta is equal to rad 2 over 2. We know that theta must be equal to pi over 4. So this angle measure right here is pi over 4. So if I were to integrate from angle 0 to angle pi over 4 of the square root of 2, this is the part of the area that we would get. And then after that, if you guys were to integrate from pi over 4 back over down to pi over 2, we would get the sum of these sectors added together, and that would then complete that area. So the setup of the equation for this one, did it say set up the integrals? An expression for the integrals. So let's do purple first. So area equals 1/2 r squared of the purple, and the purple is defined by the circle radical 2 squared from 0 to pi over 4. And then we're going to add 1/2 from pi over 4 to pi over 2 the other circle, which is the blue region, 2 cosine of theta quantity squared. D theta. Sorry, forgot the D theta. Okay, so that's the setup of that. And let me know if you have any clarifying questions on 2003. Let's see, there's a question, but I can't see the question. Okay, someone did ask to go over the challenge question. So yeah, let's go over the challenge question. Since this person wasn't here in class today, I did post Brandon's very detailed key of the problem. But let me pull up, I took a screenshot of the problem so that we could discuss it. Oh no, what did I do with that problem? Okay, give me a moment. Let me just take a quick picture of this. Okay, so on the challenge question, hopefully, so some of the challenges that hopefully you guys worked through initially was to come up with the intersection point of the two curves. So let me look up what the intersection was. So just to make sure that you guys did that correctly, when you're finding the intersection, you're gonna make sure that you guys are in rectangular mode. Sorry, it's frozen. Okay, so make sure that you guys are in rectangular mode when you're doing this, and then you're graphing it in terms of, so what you guys should see is x's. And I'm trying to draw this intersection point. So on your calculator for y1, what you should see is you're going to enter in 2x sine of x, and then for y2, you're going to enter in 1 minus sine of x, and then you're going to find the intersection point. Now there's going to be multiple intersection points. The point that you guys want is the first point of intersection after 0. So when you're taking a look at the curve and you see like one curve look like this and another curve look like this is the intersection point you want, because after 0, the first intersection point that you guys see should be this one, and that value is x equals 0.796, about that. Recommendations are, after you find the intersection point through second math, that you store that value. So that value, if you exit and go to the home screen, is stored under x. So you would hit x and then store it in alpha A. And then after that, you guys can use that stored value. Now, if you take a look at the sectors, there's 2 different regions that this is split into. The very first one, we know that at angle 0, we start off at 0 for this under part, this region that's under. And the sectors that span this section only touch that blue curve. So all the way up until the intersection point. So that means that when I integrate from angle 0 to angle 0.796, that I'm going to, since these sectors only touch this blue curve right here, it's only dependent on that blue curve. So when I set up my integral for that part, it's going to be, so area of region 1, so this is A1, is equal to 1/2 0 to your stored value of alpha A. R squared would be the blue curve, which is 2 theta sine of theta squared d theta. And then you have to set up a separate integral for the top region. And so the top region, the very first sector starts off right here at the intersection point, and then it spans out. And then by the time it wraps around to pi over 2, you get this entire region here. So the purple one, notice that the purple one only touches the red. So area 2 would be 1/2 from the intersection point, which is the angle, back around to pi over 2. And that region only touches the red, which is 4 times 1 minus sine of theta, quantity squared. And so so a couple of things, like there was some problems that we did in class where you saw that the results of the answers were combined. Sometimes you guys see that in the multiple choice where it was 2 separate integrals that were either added or subtracted together and they combined them together. That only is allowed if your limits of integration are the same. But in this case, since you guys are adding 2 separate regions with 2 different limits of integration, the only possible way to come up with the total area is to add these 2 without combining the 2 integrals. So on the calculator, if I was in polar mode to graph, I'm switching back to rectangular, or function mode, which you guys should have been in anyways for the intersection point, and then doing this integral in function mode. Hopefully that makes sense. And the correct answer when you guys combine the 2 is about 0.214. Does anyone have any other questions or any clarifying questions on the challenge problem? I'm not seeing any other questions come in. Let me know. I'm going to give you guys a minute to see if you have any other questions. I will redo the video for the one that I had a mistake for and then repost that, but I'll delete it for now. Okay, you guys ready for the test tomorrow? This isn't a very huge chapter, so I kind of think that you just have to work through some problems and see if you guys have any questions tonight. Feel free to text me on Remind. All right, guys, so I will post the answer to what was supposed to be your homework quiz for the polar, which is those 2 questions. Oh, okay, I see one question coming in. Oh, okay. So chapter 9 review, there was a question about how we know it went around the curve 3 times. So here I have a table of values and they want me to sketch this particle's motion from 0 to 6 seconds. But when you graph the curve from 0 to 2, you see that it's enough to wrap around the ellipse 1 time. So if we can continue to go from 2 to 4, that's another iteration around the ellipse. And then the third one would be from 4 to 6. So just plot the points in it and you should see it like it maps the points around the ellipse 3 times with 3 revolutions. Okay, guys, I'm going to log off, post this onto the agenda. Good luck studying tonight, and I will answer any other questions. If you guys have an urgent question that you want me to solve and that I didn't get to, just text me on Remind and I can shoot a quick video on it. In the meantime, when I get off this call, I'll re-record the video for the response on 2013. I think there might have been some typos, so I will repost that. Okay, guys, have a good night. Bye.
Thank you.
You're welcome.